Let's look at inductors. So we've seen in a previous lecture that coils and solenoids and loops have a property that's called self-inductance. Basically what happens is that when a magnetic flux changes through the coils or solenoids or whatever, they induce a magnetic field. And that property has to do with the self-inductance of these coils. Now, due to this property, these coils are often called inductors. And now we think that inductors are electronic components. So whenever I would say we're using a 30 millihenry inductor, I would think of an electronic component. I wouldn't think of a big coil of wire or a big solenoid or something like that. In a circuit, inductors look like this. They are like a little coil and have the letter L on top of them. Now, how do they behave in a DC circuit, in a direct current circuit? So here we have a little circuit. There is an inductor, there is a battery, and we have a switch. So at time equals 0, we'll close the switch and see what happens. Well, here's the switch closed, and the battery is trying to push a current through the inductor. All of a sudden, this inductor will feel that something has changed through its coils, and it will react to that. It doesn't like the change, so it will produce a magnetic field so that the induced current that produced the magnetic field matches the current supplied by the battery identically. So here is the current supplied by the battery, here is the induced current. They're the same in magnitude but opposite in directions. So for all intents and purposes, when we first close the switch on an inductor, the inductor breaks the circuit. The battery cannot push any current through here because the inductor matches that current, sends it in the opposite direction. So we'll say that at time equals 0, in a DC circuit, the inductor acts as a broken wire. Now, a long time later, we'll call that when time goes to infinity, the inductor had a chance to get used to current going through it. And it's not going to fight back anymore. So it will basically feel to this battery as if there were nothing here. The inductor just lets current go through unimpeded. It's not going to induce anything anymore because it takes a lot of effort to do that. So a long time later, it got used to all that current going through it, and now it just acts as a wire. Now, inductors store energy in their magnetic field. We had a capacitor that stored energy in an electric field. So that's the electric field counterpart of the inductor. The energy stored in the inductor is 1/2 Li squared. And here we're going to play with the math a little bit. So energy is 1/2 L. L is self-inductance, so that is the number of turns times the magnetic flux divided by the current times the current squared. So I cancel out one of these i's, and I'm left with 1/2 Ni, and the flux I will write as magnetic field times the area. So now I'm going to play some more, and I'm going to multiply top and bottom by mu naught, top and bottom by L. So basically this is 1. I'm multiplying this entire thing by 1. But the reason I'm doing this is because when I rearrange things, they will look like this. So I'm going to have the 1 over 2 mu naught over here. This mu naught is going to be there. Then I'll have N divided by L, so the number of turns divided by the length. And then I'm left with I times B, and this L I'm going to put in here. Why am I doing that? Well, because this is still 1 over 2 mu naught. Mu naught Ni is the magnetic field through a solenoid. So I have the magnetic field here times another magnetic field gives me B squared. And Al here translates to the volume of a solenoid. So it's the cross-sectional area times the length of the solenoid. Why am I doing that? Because energy density is something that will be important later on, and energy density is energy divided by volume. So if I divide all of this by the volume of the solenoid, A times L, then I end up with 1 over 2 mu naught B squared being the energy density for an inductor.